All right. So given this, we have kind of like we can link the conditional of our joint density of the mixture model to the parameters of the mixture of linear dynamical systems. So how can we ensure now that these parameters are stable? Here we use the first Lyapunov function that I introduced, which is the quadratic Lyapunov function, and we impose these constraints. So the constraint that the eigenvalues should be positive for each of the linear dynamical systems. Also, the bias should be this term, and I forgot to say, but the mixing functions should sum up to 1, but this is already given by the GMM by the constraints of the Gaussian mixture model. So the idea is, okay, let's estimate these parameters with these constraints. So we do this using proposing an optimization constraint optimization problem, which is the stable estimator of dynamical systems approach, or SETS, which is what we use. And so what we're doing is we're basically estimating, we're re-estimating the parameters of our mixture model such that they yield a stable nonlinear dynamical system. So there's 2 ways of estimating these parameters. First, we can minimize the mean square error, and this will give us something like this. For here, the red lines are the demonstrations, and the black lines are reproductions starting at the same initial point of the demonstrations. And we can also optimize for these parameters with by minimizing the negative log likelihood of the density of the joint density itself. And here we have a different. So basically, it also re-estimates the parameters, but it's a little bit more constrained, more local, because it's still trying to give us a really good estimate of our density. So it's not really changing the parameters of the mixture model that drastically as what does the mean square error objective. So yeah, so the red trajectories are demonstrations, and the black trajectories are the reproductions from the same initial states. So here we can see some examples of sets in action. So how we can use sets in which type of application. So basically reaching motions like this, and obviously if the target changes, then it's going to be robust to this change in the target, because that's the intrinsic property of a dynamical system, which we are learning. Here we have a little bit more complex example where we're actually learning a sequence of point-to-point motions. So the idea is that we first demonstrate a sequence of point-to-point motions, then we segment these, and we basically discover how many action phases, which we represent as individual sets, models, and then we execute them with the robots. So here the attractors are changing all the time in order to reach the high-level goal of rolling this pizza dough. Here you can see the attractors are these frames. And here you can see another example. One of the advantages of learning these motions and in task space is that you can learn them in one framework, for example, in one robot, and then since everything is learned on a task space with respect to, for example, the object, here all of the attractors are with respect to the object, so you can easily transfer it to another robot and have the other robot execute the same motion that you learned, but with another different robot, which is pretty cool. So here you can see that. The way that we extract each of these individual motions is part of my research, but we're not going to cover that here, so if you're interested in that, you can ask me later. Alright, so we can do pretty cool things with sets, but it has some limitations. So for example, the optimal number of Gaussians, which is kind of like the main question of just fitting mixture models in general, like you still have to set it manually or empirically, like doing model selection or something like that. And also it cannot handle really highly nonlinear motions. For example, something like this. SETS is not capable of actually reproducing this motion very accurately. Also, something like this type of motion, as you can see, where it's highly nonlinear, but the main problem with it is, do you have any idea why? No. All right. So the main problem with it is that if we see, this is the Lyapunov function that we use, right? So it's basically just a circular, like a quadratic Lyapunov function centered at the attractor. If we look at these regions, at this trajectory here, which is going away from the attractor, we can see that if we look at the vector that's given by the dynamical system, and if we look at the gradients of our Lyapunov function, it's actually an acute angle. So the dot product between these two vectors is positive. So it's basically contradicting our Lyapunov function that we're using. So what we're saying is that this Lyapunov function is a little bit too restrictive to generalize these type of motions, which are capable of kind of like going a little bit away from the attractor and then they come back. So can we do better than this? Of course, that's why I introduced the parameterized Lyapunov function. So for example here, now our Lyapunov function is some sort of like ellipsoidal shape. So if we look at the vector of the dynamical system, if we look at the gradients here, now it's in obtuse angle. So we're good, and it's capable, and it'll be capable of reproducing these motions very accurately. So there's one little complication with using this parameterized Lyapunov function is that we really don't know. We need to have a really good guess in order for us to be able to estimate, for example, sets with this. Otherwise, if we introduce this in the optimization problem, it's already a nonlinear optimization problem, so it might not really converge to like any solution. So another approach that we propose that uses parameters for the Lyapunov function is this one. So instead of learning all of the parameters, so basically the mixing function, which what I call is gamma, and the parameters of our linear dynamical system, just with the GMM parameters, what we do is we decouple this estimation, and we still estimate the mixing function with our GMM, but now we estimate the parameters of the dynamical system separately in a separate optimization function problem. So given this set of demonstrations, we followed the same approach as in sets at the beginning, but now we only learn the joint density on the position trajectories, not on both position and velocity. And then we solve a constraint optimization problem to estimate the parameters of the independent dynamical systems by minimizing the mean square error. And by imposing these stability constraints, where we include now our P matrix here. So yeah, so now we're ensuring stability with this parameterized quadratic Lyapunov function. And this problem, we actually have two approaches of solving it. So this problem itself is a nonlinear semi-definite programming problem. So there are solvers that can easily solve for this. Or we can estimate our P beforehand with another approach that I will cover shortly later. And then just estimate our A matrices afterwards. So this is what we get. So for example, so here we call the LPVDS, so linear parameter varying dynamical system approach, which was initially introduced in Sina's thesis. And so basically, this is what we do. So since it's decoupled, the parameters are decoupled. So we have two steps. We first estimate the Gaussian mixture model parameters, and then we estimate our A matrices, and then we achieve something like this, which is very similar to what we had with sets on this specific motion. But now if we compare it with these more like highly nonlinear motions, which have trajectories that are going away from the attractor, then we can see that the LPVDS approach is much better than sets in this specific case, and also in this case as well. Because here, for example, the estimated parameterized quadratic Lyapunov function maybe it's an ellipsoid like this, so it's capable of handling these type of trajectories. All right, so this approach also has its own limitations. So the same as sets, we need to have the optimal estimate of how many Gaussians you need. You either set it manually or empirically through doing model selection with the BIC metric, for example. But, so one of the difference between set is that this approach is very sensitive to the fit of our Gaussian mixture model, because we're not modifying it as in sets. So we were basically just initially estimating the GMM, and then we leave it there, and then we just estimate the system parameters separately, assuming that the GMM is perfectly representing our trajectories. So for example, here's a really good fit. So we have a really good reproduction, but here's a really bad fit, which you can get something like this, for example, with normal expectation maximization, you can get this type of fits. And it'll give us this type of trajectories, which are quite bad. So this is one of the limitations, but I mean, this can, you can have workarounds, and there are some approaches that are capable of actually giving you really good fits for Gaussian mixture models. So these are the two approaches that we have proposed in this lab, and these two are the ones that we're going to cover in the exercise session. But obviously there's other approaches that have tried to tackle this problem, which people call in literature this stability versus accuracy problem, where the stability constraints are too restrictive to actually yield like really accurate reproduction of your nonlinear motions. So one approach that tried to extend sets, which I call beyond quadratic Lyapunov function, is this tau sets approach, which is based on diffeomorphic transformations and a complex Lyapunov function. So the idea is that first, given some demonstrations of nonlinear motions, you construct a complex Lyapunov function from your demonstrations. One example of a complex Lyapunov function is something like this, which is called the weighted sum of asymmetric quadratic functions, which here we have like it's a parameterized Lyapunov function centered on the attractor, and then we have a whole bunch of other, here it's asymmetric because we're reshaping the functions. So this is basically just a way to get a quadratic Lyapunov function that's much more flexible. But the problem is that we cannot really use this, for example, directly to estimate, like in an optimization to estimate our A matrices. So that's why these guys, what they did was then they said, okay, so we estimate this complex Lyapunov function, and then we estimate diffeomorphism that transforms our data from being the Lyapunov function, complex Lyapunov function, to a quadratic Lyapunov function. And we transform our data based on this transformation. So now our data looks something like this, which basically is not contradicting a quadratic Lyapunov function. Then they learn sets on this new space, and then they transform it back to the original space, and they get some really good accuracy, reproduction accuracy. So that's basically this approach. Another approach which has been which was recently introduced is this contracting dynamical system primitives approach, which follows exactly the same formulation as sets. So it's a mixture model. The mixing function and the system matrices are represented by the GMM, and they use the mean square error as well. Everything is the same except for the stability conditions. Instead of using quadratic Lyapunov functions or the parameterized one, what they use is partial contraction theory, and then they have this other set of constraints. And they're able to reproduce like nonlinear motions that are going far away from the attractor as well, in a really good way. So here is the full list of all the references that I used throughout the presentation, if you're interested in the papers. And now we'll go on to the exercise session. So if you guys, what? Oh, do you have any questions? No questions?